Hello, I'm good. How are you? I hope you all had a nice weekend, a nice long weekend. Um, okay, so today in Dr. West's lecture, I was having some internet problems, so I was kind of like in and out. But I know that you guys were starting out with a little bit of naming, and then he talked about directing effects and multiple substitutions, things like that. So we started that a little bit last week. And now we're just going to continue and basically cover what he did in lecture today. So that's the plan for today. And people are saying they're tired, but a great weekend. Good. I mean, not good to being tired, but good that you had a good weekend. I am also very tired, so I can relate. Okay, so what we did last time is we talked about activators versus deactivators. We know that activators are electron donating groups, and we know that they make benzene more reactive. We also know that deactivators make benzene rings less reactive, and those are going to be our electron withdrawing groups. We also talked about directing effects, and we know that ortho-para directors are basically going to direct new groups to be added to those ortho-para positions, whereas the meta-directors direct a new group to the meta position. So we can put those two concepts together and we get our ortho-para activators, our ortho-para deactivators, and then our meta deactivators. We're going to talk about that a little bit more in a second, but I'm just going to flip over here. And I don't want to draw all of these guys out, so I pre-drew them for you. I thought it would save some time. So our activators are going to be anything that has a lone pair, anything that has R groups, things like that. Exactly the same as when we did Diels-Alder. And our deactivators are going to be anything from halogens, carbonyls, cyanide, NO2, right? And anything with a plus sign, obviously. And the reason I put this in a specific order, saying from most to least reactive, is because you will actually have to know this order a little bit, like at least in general. So you have to know that the strongest activator we're ever going to talk about in this class, oops, I dropped my pencil, is NH2. So I'm going to say this is the strongest activator. And the strongest deactivator we're going to talk about in this class is nitrogen with a plus. You also have to know that R groups are weak activators, but they are activators. And you also have to know that the halogens are deactivators, but they're still ortho-para directing, so we call these guys weak deactivators. And you don't necessarily have to know the order of all the halogens, just know that they're in between the activators and the strong deactivators, which are these guys. Any questions so far with what we've talked about? The reason this benzene ring is here is just to show you that anything this way from the blah, blah, blah. Anything this way of the benzene ring is going to be activating. Anything lower than this is going to be deactivating. Okie dokie. So let's go back to the handout. We talked about Friedel-Crafts as well. I'm not going to go into all the stuff about Friedel-Crafts again. I just want to mention, remember that Friedel-Crafts does not happen if there's a strong deactivator or NH2 on the benzene ring. So that being said, if I were to give you a reaction like this, we know that this group right here is a strong deactivator, and this is a Friedel-Crafts reaction. So we automatically know there's no reaction here. The same exact thing can be said over here, except now we have NH2, and we know that NH2 is an activator. However, this is one of those exceptions. So Friedel-Crafts does not happen with NH2. Oopsie. And I'll write a little note. Too basic. So it's so basic that it's not able to do a reaction. And for that reason, we get no reaction. So I'll zoom out a tad. Does that make sense? That general concept? Yes? Okay, super. So I will give you a moment if you need to take a screenshot or write something down. All right, so I'm going to zoom down here. And now we're going to have some practice with those withdrawing and donating groups. So for A, we see that this is the substituent. Is this a donating, is this an activator, a weak deactivator, or a strong deactivator? It is a deactivator. Is it strong or weak? What do we think? And someone asked about yesterday's SI session. There was no SI session yesterday. Everything was closed for 4th of July. And yes, I agree with y'all. It's going to be a strong deactivator. How about for B? Is it going to be an activator, a weak deactivator, or a strong deactivator? Strong deactivator. Someone said it would be a strong activator, so let's look at this one. It's the same exact functional group, just attached backwards. So this is one of those tricky ones where if it's attached at the carbonyl, it's a strong deactivator. If it's attached at the oxygen, it has those lone pairs. So here it actually becomes an activator. I saw an O, so I hope that makes a little bit more sense now. Okay, so what do we think about C? This big old ugly thing. If we wanted to write it in condensed formula, this would look like SO3H. So yes, it is a strong deactivator. Cool. What about this guy, which looks like so? I agree, another strong deactivator. Cool. And last but certainly not least, what about bromine? One person answered, but I want a couple more people to try. Weak deactivator, yes. Oopsie. Awesome. So which of the following can undergo a Friedel-Crafts reaction? F, and one more actually. And D. Yep. So both of these guys could undergo a Friedel-Crafts reaction because it's not NH2 and it's not a strong deactivator. Cool. I'll leave this up for a second. All right. We already talked about this, so we're just going to go ahead and skip. We also talked about this. I already showed you that. So I'm just going to show you this. This is the exact same thing I had written in my table that I showed you at first, but I believe this is the picture I got right from his PowerPoint. So I strongly suggest looking at this and remembering the order. The biggest ones that I think are important: know where NH2 is, know NO2, CN, SO3H, and then just know that these are kind of like in the same bunch. So those are kind of in the same group. And someone said to zoom out. So I didn't draw in like the answers to up here, but I can zoom out if you would like. Do, 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 do. Okay, for what we did before, yeah, that's fine. I can go back here. Let me know when you're good to go. So D is a activating group, and so for activating groups, we don't have to label it as weak or strong because they're all pretty much the same. But we know that D is, if we look back over here, it's fairly weak. It's towards the end of the spectrum. But again, activators are activators. We don't discriminate strong or weak. So, in case you still need that. Are we good to go? Yes? Okay. Cool. I don't know what I'm saying anymore. Alrighty, so now that I've told you all about this stuff, let's actually do some practice problems. And there's pretty much like a set of steps that I like to go through when I do these reactions. So I'm going to zoom in, and as always, I will zoom out at the end. So first and foremost, what kind of group is this? Activator, weak deactivator, strong deactivator. What do we think? So yes, we're going to call this an activator. Cool. And what kind of reaction is this? A bromination. Cool. Or we could also just say halogenation. But you guys were absolutely right. It is also a bromination. And when we do a halogenation, what do we add to the benzene ring? Just a halogen. Yes. Okay, cool. Just making sure. All right. So when we have an activator, where is this going to direct? Ortho, para, or meta? Yes, so it's going to be ortho and para. So I'm going to go ahead and draw an arrow if my iPad would let me. That would be so cool. Okay, there we go. Sorry for that. So this is ortho. This is ortho. And this is para. So we're actually going to get two different products. And the methyl is not going to change. It stays exactly the same. But what we are going to have is a bromine. And we will have one bromine in the ortho position. And we can have another answer where the bromine is in the para position. We also could have put the bromine here, but we would have gotten the same exact answer as this, just flipped this way. So those are identical. So this is how I want you to approach these kind of questions. I don't want you to go through the whole entire mechanism. I want you to think, what kind of reagent do I have? What am I adding? And then figure out what kind of substituent it is. So where am I adding? So you just want to know what and where, basically. So for the next one, what kind of reaction is this? And I'm going to do it red in a different color so it sticks out more. What kind of reaction do we have in this second one? A sulfonation, or sulfonation. And what group do we add in a sulfonation? Close, it's not an SO3, it's actually SO3H. And that is important because sometimes he will give you an answer that has an SO3 and another answer that has an SO3H, and people pick the wrong one. So careful, this is one of those tricky ones. All right, and NO2, is this a weak deactivator, strong deactivator, or is it an activator? Strong deactivator, I agree. I'm going to do it. Okay, so a strong deactivator is going to direct where? Meta, awesome. So we're going to direct here and here, but our two answers would be exactly identical, so I'm just going to draw one of them out. So we get, let me be consistent with these double bonds. NO2 stays exactly the same, and we end up adding to the meta position an SO3H. Ta-da! Any questions? Okay, cool. It doesn't look like it, which is awesome. All right, so for number 3, what kind of reaction is this? An alkylation. Ooh, okay. Ooh, and someone said chlorination, which I'm glad you actually said that. This tends to be tricky because we have the chlorine here, but remember two things. If we have an alkyl halide, that's your hint. So the alkyl halide is a hint, and the AlCl3. So the AlCl3 is always going to be the acid in a Friedel-Crafts reaction. So we know that this is in fact Friedel-Crafts alkylation. And what is the electrophile in a Friedel-Crafts alkylation? And we can be more general. An alkyl group, but even more specific than that, the electrophile It's something important. A carbocation, exactly. And the reason I make such a big deal out of that is because I always like to number 1, 2. And I know I would have this carbocation right here. Carbocations can undergo rearrangements. Specifically this one. Can this undergo any kind of rearrangement? No. Perfect. So we know that this is going to be added to our ring. All right, next step, we're going to see, is this an activator, a weak deactivator, or a strong deactivator? Okay, we got a couple different answers. So this is actually a weak deactivator, because remember, all halogens are weak deactivators, which means they direct where? Orthopara, exactly. So that's why they're kind of special. They're deactivators, but they still direct orthopara. So we're going to get 2 different answers. And our answers will, excuse me. I wish I could draw a not ugly benzene ring, but it doesn't seem like today is the day. All right, so chlorine, of course, doesn't move. And we could have added our carbon chain here. And 1, 2. Or it could be added here. 1, 2. Just fix that. And yes, this will be uploaded today. All right, so the last one in this set. What reaction is this? Yes, exactly. This is the Friedel-Crafts Alkylation. And we know that because of the acid, and we also know because of this group. And I want to just see if you guys remember what the electrophile is in this reaction. I'm going to draw it out here, and I want to know if you remember the name of it. Yes, you're correct. Melanie, you gave the right condensed formula, but the name of it is the acylium ion. So remember, this is one that you have to know by name, and it looks like so. These are the 2 resonance structures. Alrighty, so let's go ahead and define this group. Is it a activator, a weak deactivator, or a strong deactivator? It is a deactivator, but is it strong or weak? What do we think? Okay, so a couple people answered, and yes, I have to agree, it is a strong deactivator, right? It's the weakest of the strong ones, so I see where people might have gotten confused. But remember, everything besides halogens are strong deactivators, and carbonyls do count. So if we scroll back down, Where do strong deactivators direct? Meta. Cool. Meta. But is there any problem with this reaction? Probably, because I said it like that, right? Yes, someone got it. There's a strong deactivator and a Friedel-Crafts. Can that happen? Hell no. You right. Okay, so this is actually going to be no reaction. Dun dun dun. All right. Ta-da! Any questions on these guys? We got that. We got through that super fast. You guys are killing it. All right, I haven't gotten any questions yet, but I am going to leave it up for a second so you can. Okay, so why was that last one no reaction? Great question. Basically, Friedel-Crafts reactions are not going to happen if there is a NH2 or a strong deactivator on the ring. And I will actually pull this up so you can look at the visual while we talk about it. Yeah, exactly. So if there's a strong deactivator on the ring, it's not going to happen. NH2 is a really, really strong activator. The reason that doesn't work is because it's very, very basic. So don't get confused. NH2 is not a strong deactivator, but it's still not going to work in Friedel-Crafts. Okay, so scroll back down. Does anyone still need this? And it occurred to me that this looks like just 2 oxygens, so I'm just gonna make it abundantly clear that that's a plus sign. Ta-da. Okay, if anyone needs it, please let me know and I will be happy to go back. So now, actually, I'll stay up here for one more second while I talk. So, as I mentioned last time, this chapter has 3 layers. So the first layer is just a regular old substitution, right? An electrophilic aromatic substitution. You have to learn what the different reagents are and what the different products are. Cool, you guys mastered that. The second step is learning about activators and deactivators and directing effects and learning how to do 2 substitutions. So having one thing already present on the ring and then doing another reaction. So you guys are at level 2, you did it, we're good. The next step is multiple substitutions, such as this. So what happens when we have multiple things already on the ring? That's going to be like the level 3. That's the hardest part of this chapter. And so we're about to start that. If you have any questions on the first 2 levels, pretty please let me know now. And while you come up with questions, I'm going to go back up to page 3, I believe. This one right here, Friedel-Crafts. And now that we've done the stuff and we're not behind anymore, I do want to go back and answer one of these questions. All right. So this is a Friedel-Crafts alkylation. And when we talk about the alkylations, we're going to do the rosemary method where we kick that off and we add a plus. So we end up with this guy. Is this the best carbocation that we could have? No. So what kind of rearrangement can we do to make it better. Dang, guys, you're so much more ahead of all my tricks and games. That's absolutely right. We can do a ring expansion. So I find that a lot of students forgot to do ring expansions, or they didn't actually like learn how to do it in Orgo 1. So I'm gonna go ahead and do 1, 2, 3, 4, 5, 6. And I'm also going to draw out the hydrogens. Ta-da. I know it looks messy, but we're essentially, I'll draw it again on the side. We're essentially going to take this carbon and attach it to here and form a 5-membered ring. So we also have to break this bond. So we get a 5-membered ring, and we're going to call this 6, 5, 4, 3, 2, and we have a methyl coming off of here. And the way I came up with those numbers is this was 6, right? And we know that 6 attaches to 2, so that's where we get this bond, and we get our methyl over here. And now we have to figure out where our plus goes. So we had 2 hydrogens on 6, 2 on 5, 2 on 4. We had 1 hydrogen on 3. We had 1 hydrogen on 2. And we had 3 on the methyl. So, which carbon has the plus charge? I'm also going to just move these numbers so they're not like super duper in the way. So which one of these carbons has the plus sign? So one person said carbon 2, one person said carbon 6, one person said carbon 2. So what you're really going to look for here is which one of these carbons does not have 4 bonds. Carbon 2 used to have the plus sign, but it has 1, 2, 3, 4 bonds now. So does carbon 6. Carbon 3, though, has 1, 2, 3 bond. So it has to have a plus. And I got an oh, so I hope that was like a light bulb moment. Okay. So this was our ring expansion. And someone said they're lost, so we can do it again in 1 second. My screen got dark for a second, but I guess it's not darker for you guys. Okay, so let's just start over here. If we have this molecule, right? We want to expand this and make a 5-membered ring. So the way we're going to do that is this carbon is going to, I don't want to use the word attack, but it's going to attack this carbon, break this bond, and make a 5-membered ring. So we're going to call this carbon 1, carbon 2, 3, 4, 5, 6. So I'll start drawing from carbon 6. Carbon 6 is attached to carbon 2 now. Carbon 2 is still attached to carbon 3. Carbon 3 is attached to 4. 4 is attached to 5. 5 is attached to 6. Carbon 2 has carbon 1 coming off of it. And we didn't do anything to the hydrogens. So we're going to keep the exact number of hydrogens each carbon had, right? So carbon 2 had 1 hydrogen, carbon 3 had 1 hydrogen, carbon 4 had 2, carbon 5 had 2, carbon 6 had 2. Now that we've filled in all of the hydrogens, we go through and see which of these carbons don't have 4 bonds. So we have 1, 2, 3, 4. That one's good. 1, 2, 3, 4. That one's good. 1, 2, 3, 4. 1, 2, 3, 4. But then this guy has a plus charge. Bam. Okay, so hopefully that's a little bit better. And so I'll keep this drawing just in case it's easier to see, but I'm going to move it up here so we can do our reaction. Okay, so we know that our new cation looks like so, and we know the benzene is going to attack it, right? And so we end up getting a benzene ring with a 5-membered ring attached, and that 5-membered ring has a methyl on it. I know this looks super complicated, and the first time you see it, it looks really ugly, but wink, wink, nudge, nudge, Dr. West really likes this ring expansion question. And so there's a good chance, there's a good chance you will have to do a ring expansion on the exam. Any questions, comments, or concerns? Someone said I definitely have to rewatch this session. I get it. I really do. This is a lot, but hopefully you know a little bit more than you did when you came in. And it's planted like a seed. And next time you watch it, it'll be a little bit easier to understand. It's slowly clicking. Hell yeah, dude. Okay, so someone said they have to go. Bye-bye. I did send the attendance one more time in case anyone needs it. And we are going to go back all the way over here. For some reason, the page numbers aren't here. But we are back on this page with these examples. And since we have like 5 minutes left, we're going to do a couple of these. I know we jumped around a little bit today, so I'm sorry if it confused anyone. Okay, so when we have multiple substituents on the ring, I'm going to do a little notes. When you have multiple substituents, you're going to define each one. So figure out whether they're activators, deactivators, strong, weak. Could you not? Thank you. And then the strongest activator or weakest deactivator controls, I spelled controls wrong, and that's going to control the next, or I'll say directing effects. So let's see what in the world I mean by that. For this first guy, we have two substituents, and I'll actually do them in two different colors. The blue substituent, how would we define that? Is it a activator, strong deactivator, weak deactivator? What do we think? Strong deactivator, absolutely. What about the yellow one? This one is also a strong deactivator, absolutely. Uh-oh. So now we're kind of in a predicament, right? Let's pull out this guy. So we want the one that is the strongest activator, aka the weakest deactivator. So when we look at here, CN is over here, N plus is over here. So between the blue and the yellow, which one is going to be in charge of directing effects? The blue, absolutely. So I'm going to put a little star by blue because that's the one that controls the directing effects. And we know that strong deactivators are going to direct where? Orthopara or meta? Perfect. Okay. So what this means is that we're going to substitute meta to this group. And that would be 1, 2 right here. And 1, 2. Uh-oh, this one's already taken. So there's only one possible answer. And that would be oh, and just in case it wasn't clear, I know it's written here, but it's kind of small. We're doing a halogenation for each one. So for each of these examples, I'm just going to go ahead and add a bromine for consistency. So in this first example, the bromine will be added right here. I know this was kind of a step harder from what we've done before, but it kind of takes all the concepts we've already done and it takes it one step further. So how does everyone feel so far? Ooh, so okay, someone said 3.2. So let's say 0 is I'm absolutely completely lost. I don't even know what a benzene ring is. And 5 is this is swag. I completed the whole handout already. I'm Gucci. How do you guys feel? 4.5, hell yeah. 3.7, cool. Someone said 3, awesome. 3.5, killing it. Okay, so I'm super happy no one's at a 0 or a 1. 2, that's okay. No need for a sad face. I know it's frustrating. It really is. But if you watch this 1 or 2 more times and kind of look at the material over again, I think it'll start clicking. This is definitely a harder section that we've done before. And I think this is the hardest chapter we've done before. So don't be sad if it's not like at a 5 yet. That's completely okay. And also, I am always open for questions. If you want to email me a practice problem you don't understand or bring it to tutoring, that's perfect. I will absolutely help you with that. But I'm proud of each and every one of you. I don't think I said this semester, but I always, in my intro, say, like, I'm your supportive mom for the semester. So, that was my supportive mom rant. It is 12:20, and I don't want to keep y'all here too long ahead of time, or too long past time. I don't know. English is hard. Do you have any questions, comments, or concerns before I let you go for the day? You're very, very welcome. And yeah, I'll try to upload it like right now. Sometimes it takes forever to load, but hopefully it won't. If you haven't signed in the sign-in sheet, pretty please do that for me. You're very welcome. Have a wonderful day. Aw, y'all are too sweet. You too. I hope y'all have a great week.